Okay, so I'll just start here. I hope you've been watching the videos on the YouTube channel. We're almost done with the chapter 10. So I'm going to finish up the last part of chapter 10, so we can move on to chapter 11. Then we're going to finish up the all chapters by this coming Monday. So we can do some good review session for the exam too. Okay. So the second part of chapter 10, we just tried to make a alkyl halide from alcohols. Okay. So for this one, we actually use the similar rule we have learned in chapter 10 for the others. If you have methanol, it's a methyl alcohol, and also we have primary alcohol here, and also we have secondary, then we have tertiary. So this is the types of the alcohol we can have for the reaction here, and we'll do this. We can find a trend over the alcohols with the reactivity trends. Okay, so basically what I mean by that is whenever you have a hydroxyl group over here on the compound, they consider as alcohol, and whenever you do the HX form, like with the hydrogen with the halogen group HX form, what you can get is this will be replaced by halogen, and then as you can see, these two will make water. Okay. So what I mean by that, this one and this reactivity trend is if you go have more substitute carbon high order in your alcohol position right here. So this is primary, secondary, tertiary alcohol. This is methyl, methanol. Then if you go from left to the right, you're going to have this reaction is more frequently happening or faster. Okay, so this is the something we can know from the experiments. So if that is the case, this is why tertiary alcohol will do some really good reaction with the HX form. So if I give you this one over here, right? I can try to look at this alcohol in a tertiary position. Those are three, right? So this reaction will happen quite vigorously, really fast. So if you can do this with the HCl and the ether solvent molecules, you can probably have this easily get this. Why? Okay. So whenever you have a more substitute higher degree of the carbon, then we can find the hydroxy group is tertiary or secondary kind of alcohol there. Then we'll work really easy with the HX form, which is the hydrogen and halogen in some organic solvent like ether. They're going to give you substitute right here. So this will be substituted by halogen, giving a water here. Okay. Makes sense, right? We good? Okay. So tertiary is better than secondary, secondary is better than primary, and so forth. Obviously, the worst one for this reaction would be methyl. So if that is the case, sometimes we need to know what might be the better way to do this type of a reaction. If you have only secondary or primary type of compound. So for example, if you have this type of compound, this is only secondary. So in this case, uh, uh, there's some alternative way to do this. We can do this like a thionyl chloride, something like this one. They can do the same here. If you do treat this one here, you can have this. So once again, this is replaced by halogen 2. Right storage is this. This is one way. So if you use some alternative way to do the same job, you can do it with the thionyl chloride over here. And also, there's another way to do that too. With the other alternative way, what you can do is, if you have also like a secondary, like two button over here, you can try to do it with the phosphorus tribromide here. With also the organic solvent like ether, they can also do the same. Pretty much here. So for tertiary, so simply if you use HX form is good, but if you have a secondary or primary, you see the direction will be lower because of the trend we saw before. Those are the two alternative ways that you can do this in here. Okay. Makes sense, right? Okay. So simply, those all methods are just going to be used for replacing your hydrogen group and the halogen groups in here. Normally, they're all really good for HCl, hydrobromic chlorate ionic solution is pretty good. But this one, the fluorine is not really working well so much. So you have a bit of a special condition to do this. Either you can do this way, or you can also use the diethyl aminosulfur trifluoride, but this one you don't have to know, because this is the kind of not common, because this will not be so common in this type of alkene halide formation from the alcohols. But this is just for your information. We good? Okay, perfect. So let me move on. So that kind of makes sense. That also goes with the other general trend we saw in other example in chapter 10. The next part is the we call Grignard reactions. So the Grignard reagent over here. So what you can do simply is, whenever you have some kind of a hydrogen group attached to your organic compounds, like the alkyl halide, something like this one, you can treat it with the magnesium and some organic solvent like ether. Okay? So if you do this one here, what happens to this one is they actually try to do it. This is kind of funny thing. So because I'll tell you, this actually comes in the middle. So what it does is they will show you some kind of a weird interactions, something like this one. Obviously, there's the metallic ones over here. They're going to have a bit of more weird bonding here. Eventually, they come in the middle of these two. They just now you see the magnesium in the middle, and what they do is because the difference in the electronegativity of carbon and the magnesium over here, this will become very polar covalent bonds. Okay, so they give you some sort of a R magnesium, like halogen type of form over there. Okay? And then eventually, what they do is they eventually kind of make a more like a salt type of the interaction there. So the bond will actually goes on to the carbon. So those goes to the carbon. So that becomes a negative charge, which is quite uncommon. We call this carbanion. This is carbon with a negative charge, and this will obviously become this one. So this is more like a, now it's more like I can't say, like this type of form, type of thing. This is more like a salt, like you see like a sodium and chlorine, they make plus and negative charge. We also kind of do that with the type of organic compounds here too. So those two type of things, we call this organometallic compounds. Makes sense, right? So it's a simply organic compounds and the metal will do some kind of a special bond doing this one. Then you will see this one as like organic organometallic compounds. So whenever it happens here, what you can do is you can treat it with water. But in this case, water kind of will behave like a weak acid. So it's going to grab hydrogen, this here, and this one will become hydroxide anion and then bond to this one. So eventually you're going to have, see this one is added to here, okay, and this one will make sounds good? You good? Okay. So basically what it really does is replacing the kind of a bond between the halogen group and organic is coming into somewhere between, and then makes this type of form. And then if you treat with a slightly acidic solution, you're going to have a carbanion will grab the hydrogen from the water or acidic compounds that gives the like OH the bond to the remaining magnesium halogen groups. Make sense? Really? You good? Oh, so just give you one more example here then. So if that is the case, maybe you can have this type of compounds over here, right? You can also try to treat with the magnesium over ether with some organic solvent there. And then you're eventually going to have right? Makes sense, right? And then they eventually become like this, okay? And then they grab one from the water or any acidic compounds, which is just this one. Because this is hydrogen. So if this is the hydrogen, you're going to show it. So eventually become this one. Makes sense, right? Okay, I'll move on. Can I move on? Okay, perfect. So this is one good example of organometallic compounds. So whenever you have this type of reaction, we can do a little bit more with this type of compounds here. So the first thing, and the next one, first thing is Kierman reaction. So whenever you have two, like methyl with lithium, you can treat it with some kind of copper, one iodide here. Okay. So there will be two methyl lithium here interacting with the copper 2 or copper 1 iodide here. Eventually, what they do is they're going to have a 2. I'm sorry. So there's a 2, right? That's why I put number 2. 2 methyl here. So just gonna put it this way. 2, and this is the replaced by copper. Copper, and with 1 lithium here. Okay, and then there'll be 2 lithium too. So another lithium goes with the iodine. So the lithium iodine over there. Okay, so do you see this one? There's a 2 coming in. So this one goes in here, and this 2 goes with this one. So this makes this type of product from Gilman reaction. Okay, so it makes sense, right? So you don't have to know the mechanism. This will be covered in, I think, chapter 17. Are you taking Olga 2? Yeah, so you get it there sometime soon. Because it involves with some kind of coordination kind of model. You need to look at it. So textbook actually doesn't specifically mention it. You don't have to know. But eventually, what happens to those two will be just making lithium di. We put di because it's also organic groups. Di organo copper. And the lithium iodide. But this is not so important. This is the one we need to really carefully look at. So whenever you have so chapter 10 is about, any compounds with halogen groups. So if you have this type of diorganic copper with the lithium pair up, what they actually normally do, so maybe example we can use this one. We can use this one as with the compounds with the halogen groups. Here's the thing: whenever you have like R2 copper and lithium, the halogen group will be replaced by one of this one. So in this case, this is what? Methyl groups, right? So this iodide group will be replaced by methyl. So eventually, I'm going to have this one. This is all you need to know for the exam. Makes sense, right? This is how we can do some organometallic coupling reaction with the product we can get from the Gilman reaction. So whenever you have some halogen group on the compounds, there will be diorgano, means there will be 2 R groups coming with the copper and lithium, but only one of the R group will replace where you can find the halogen group previously in the reactant, and now in the product that will be replaced by that R group. In this case, with methyl. So this iodide group will gone now and replaced by a methyl group. So this is the very famous organometallic coupling reactions using the product from the Gilman reactions. Makes sense, right? It does really make sense? Wow, perfect. I'm so happy. Because this is kind of one of the hard subjects to understand, because normally the metal, transition metal, usually transition metal, or those type of lithium or alkali metal, when they do come into reaction with the organic compounds, it gets really complicated. But this is one of the famous reaction we cannot miss. So we just slightly had a touch on the subject. So anyway, if that makes sense, we're technically speaking almost done with the chapter 10, because we only have the sub-chapter of the chapter 10, which is what we already know. So it's actually just a kind of review. So the last part of chapter 10 talks about the oxidation and the reduction. Okay? So oxidation simply means what? They're going to lose electron, right? They're going to lose electrons. Reduction means they're going to gain electrons. Okay? So technically what it means is oxidation is the, like whenever you have like a copper here, I'll show you the, yeah. So if you have a methane here, if you remember, you can treat it with some chlorine, right? And then they're going to have chloromethane, HCl over here, right? So in this case, if you look at this one over here, this one will actually going to have 4 hydrogen are covalent bond to this carbon right here. But electronegativity wise, hydrogen is a bit lower than the the carbon in electronegativity. Means when the carbon is surrounded by a lot of numbers of hydrogen, they tend to have a more electron densities concentrate into the center. Because this is a bit lower in electronegativity, meaning they don't have much power to put the electron toward themselves. Meaning, in other words, the carbon will have a stronger power to put the electron toward themselves, right? So if this is happening, this is pretty much electron density center around the carbon rather than the surrounding hydrogen here. But whenever you do this one, you have chlorine instead of hydrogen attached to the carbon. Now chlorine is a bit stronger than, much more stronger than electronegativity than hydrogen. So there will be much more pulling power to this way. Then in this way, carbon will have some ability to pulling the electron toward the central carbon. So this will goes within this category. So it's not like a losing an electron more like in a number wise, but for like electronegativity kind of force wise, because the chlorine takes more stronger force to take it electron toward this way, carbon will be, relatively speaking, oxidized. So this is a good example of oxidation. So I'll make it much simpler way. When organic compounds make a bond to hydrogen or break the bonds between carbon, oxygen, or carbon, halogen, certain things, which is electronegatively very active. This is going to be reduction. So whenever it makes the bond to the hydrogen, or when they break the bond between carbon and oxygen, or carbon and halogen, or anything that with the electronegatively kind of active element, that carbon will have a much stronger force to pull the electron to themselves. So it'll be like, it's more like a gaining electron, it's a reduction. But in this case, we break the bond between carbon and hydrogen, and also we put it in the much more electronegative elements to it. That makes oxidation. So oxidation is totally the other way. So when you break the bond between carbon and hydrogen, or if you try to make the new bonds to like oxygen or halogen that is electronegative, that will make this compound oxidized. So we call this oxidation. So this is the, if that really kind of confusing you, only thing you have to know is the bonds. If it made a hydrogen bond with this, if you break the hydrogen, carbon-hydrogen bond, it's oxidation. And the halogen and oxygen, nitrogen, all the other way. Kind of makes sense, right? Okay. Let's just move on to next example. So if I give you the Grignard reaction again, maybe you have this type of, I'll just draw this. Okay. You have this one here. You got a Grignard, the mechanism, ether, and also the water or any weak acidic molecule, that's fine. And eventually, you're going to have this one replaced by hydrogen, right? Because okay. So if that is the case, like the Grignard reaction will be reduction, because initially the carbon were making bond to the bromine, which is much more electronegative than carbon. So electrons actually going on much on this way, meaning this compound kind of losing electron in the first place. But they break the bonds and they actually create the new carbon-hydrogen bond that makes more now. Carbon has more power to pull the electron to themselves. So it's more like a gaining electron into the compound. So we call this reduction. Kind of makes sense, right? So Grignard reaction will be reduction reaction, because we're putting the hydrogen instead of the electronegative element like bromine. So this is a good example of reduction. Just a couple more examples. So whenever you have, this is also what we learned before. Whenever you have alkene, right? And you can try to brominate with this, the X2 groups, like bromine 2, like bromine molecules over there. And then elements actually. But anyway, so when they goes in, you can have a sort of a this type of bromination here. And in this case, can you actually guess what happened to this one? So this is now alkene. There was just the carbon, hydrogen here. But we didn't break the bonds, but we make the bond between carbon and bromine here. So there's the carbon and bromine here. Do you think it will be reduction or oxidation? Think about the bromine is more electronegative than carbon. So the electron will heading more to now bromine rather than carbon. So it's more like they kind of losing the power to put the electron to themselves. So it's be reduction or oxidation. There will be oxidation, because this is much more electronegative than carbon here, right? So electron goes to this way. So you said it's a reduction because you cannot view this one as a bromine perspective, but you always put your subject, object is your actual compound. So in the compound wise, in the view of the compound, they actually making having a less force to pull the electron. So this is actually they're kind of losing the electrons. It's actually oxidation. Makes sense, right? Okay. So let me give you the tricky one then. See, we have a same one. This is also what we did before. Whenever you alkene. Now not just the X2, but how about HX? That meaning we're actually going to put the hydrogen and bromine now here in this case. Okay. So if that is the case, this is kind of tricky because you had a carbon that making a new bond to the hydrogen, which is reduction, right? Because the electronegativity of the hydrogen is lower than carbon. But here, you have a making bond to the electronegative element like bromine, so this is actually oxidation. But this will happen at the same time when you treat with the HX over here, like a hydrobromic acid, hydrochloric acid, hydrogen, and so forth, right? In this case, there's no oxidation or reduction because it's cancel them out because they happen at the same time. So you don't have to specify this reaction either as reduction or oxidation. That's totally. So it's kind of tricky one, right? But only thing really you have to know is when compounds make a bond to the hydrogen, there will be reduction, or break the bond between carbon and oxygen, or the halogen groups, then it's the reduction. But when they actually break the bond between carbon and hydrogen, there will be oxidation. Or they make the bond to the halogen, there will be oxidation as well, because they're going to put the electron toward the halogen or electronegative element rather than the organic compounds. Did I say it right? Yeah, it makes sense, right? Let me actually, yeah. So this is why this carbon making a bond to the hydrogen makes reduction. This carbon making electronegative element like a halogen, it will make it oxidation because the electronegativity terms it determines either they're going to lose electron from the compound oxidation, they're gaining electron toward the compound's reduction. Hope that makes sense. We're good? Okay. Alrighty. So then, okay. So the really good example problem you may see on the exam is actually this one. If you have alkene, you have like alcohol, you have a ketone, you have an alkane over here. So maybe in a question like something you may see on the exam, I might ask you order those 4 compounds in order of, order of increasing oxidation level. Okay, so meaning the least oxidized compound will be on the left, the most oxidized compound will be on the right. So in this case, all you need to do is very simple. Obviously, these two are somewhat oxidized for sure because of the oxygen here. This is alkene, kind of tricky, but this will be the least oxidized or the most reduced compound ever because there's all fully saturated with the hydrogen, right? So that means what? They're going to have a fully reduced with a lot of hydrogens around it, which is alkane. So I'm gonna put this one over here, okay? And then those 3, I can show you there's some way to do it in more mathematical way. So if you do alkene, just draw the Lewis structure. Okay? So in this case, because of the double bond, if this was a single bond, right, it could have been like this one, right? But because of the alkene, because of the double bond, there's the 2 less hydrogen there than alkane 1. Okay? So this is kind of something. And like I said, if you have less numbers of hydrogen, and that's better. But what you can do is just try to count the numbers of the hydrogen. Okay? So that is 6, right? There's 1, 2, 3, 4, 5, 6, not 8 because of the double bond, right? Here we have 1, 2, 3, 4, 5, 6, 7, 8. There's 8 hydrogen over here. So obviously this is for sure the least oxidized or most reduced. But this is 6. Whenever you look at the alcohol, okay, so draw the Lewis structure first, and then just same thing, just count the number of hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, right? There's 8 hydrogen over there. But the thing is, you have oxygen that will make this one somewhat oxidized. So this case, you have, whenever you have oxygen, do -2. So consider this one as like a 6 hydrogen is over there for this one, which is tied with this one. Okay? So then we can put those 2 compounds as tied. They will make this one most oxidized because this one. If you have a carbonyl groups over here, you have a 6 hydrogen over here. But you have oxygen, so 6 hydrogen minus 2. That's 4. Okay. So that will make the most oxidized because that has the less numbers of hydrogen. So think about it. When you make a bond to the hydrogen, that will be reduced. But this one that has the lowest possible number of the hydrogen among those 4, that means in other way, it's not much reduced, it's well oxidized. So If you have more numbers of the hydrogen attached to the organic compounds, will be the one that is most reduced, meaning the least oxidized. The compounds that with the fewer number of the hydrogen will be the one that is most oxidized. In the other word, is least reduced. So if you kind of think this as a kind of confusing, you just need to count the numbers of hydrogen and just count the numbers of the oxygen or the hydrogen groups and see how it can be oxidized or reduced based on this one. But for your exam, this type of the example problem would be very something you're gonna see on the exams. Makes sense, right? So if I just give you a quick could you tell me which one is more reduced? Either, yeah, perfect. There you go. That's it, really. Just try to count the numbers of hydrogen and see if there's any oxygen and other electronegative elements to do some but that's pretty much it. All right, so we're done with the chapter 10. And then in chapter 11, we're gonna talk about some, I don't know if you heard before, SN1, SN2, E1, E2, of a very famous mechanism that we learned. But even today, previous chapter like 1 through 10, we already talked about this so many times. You just didn't know which one was SN1, SN2. We're gonna talk about how we can distinguish those different type of reaction as like SM1 or SM2 or E1, E2 by looking at how it's happening in multiple steps, one step, and like a unimolecular, dimolecular sort of things. But don't be afraid of just doing chapter 11. It's just pretty much everything we done already is we know. We just need to know how to do it in the different categories and stuff, classification. That's all. So I'll just stop here. Hopefully I can finish up the chapter 11 by this coming Monday, and then please make sure you watch like we did for the exam 1. Try to watch the last 2 lectures before the week of the exam, because week before the Thanksgiving. There will be the review session. Okay. Thank you, guys.